introduce you some basic concepts about Maxwell equation and the wave equation. We know that a plane wave can be described by a function of this form. A plane wave looks like this. You can treat this as one component of the electric field in the electromagnetic wave. So here A0, here A is a real and a positive quantity. Okay. And we know that this can be written as exponential I omega t minus I k of r plus delta. Okay. I can write it like this. So this can be written as A exponential I delta times exponential I omega t minus k dot r. This. Okay? So we can further simplify the representation like this. Okay. So this can be written as psi c r t. Here psi c r t is written as A C times exponential I omega t minus k dot r. Okay. Here AC is this coefficient. In general, it is a compact number. This in general is a complex amplitude.所以你看，我们对于一个平面波呢，我们可以找到它的一个对应。就本来这是平面波，波的振幅是实数。但是我们可以找到一个跟它对应的复数，然后用这个复数去代替原来那个实数。那当我们需要的时候，当我们需要知道原来那个实数的表达式之后，只要取它的实部就好，取它的实部。好，so for a plane wave, monochromatic wave, 它是一个 monochromatic wave propagating in certain direction. 考虑波的问题的时候啊，波其实是各种各样的啊，满足波动方程式都是波啊。但是我们在这些所有的波里面，我们可以选一种最简单。最简单的是什么呢？是单色波或者单频波，啊，就所谓的 monochromatic wave。那 monochromatic wave 就是单频、单色的，或者是就是单一频率的啊。那单一频率的时候呢，也会有单一的波长。然后通常我们还指定它传播的方向。好，当然你如果不指定传播方向，单一频率的波有可能是球面波，有可能是柱面波，可能其他各种的，只要是单一频率就好。或者是单一频率，你也可以把不同方向传播的平面波叠加起来，它也是单频波。好，但是我们现在所谓的平面波是指单一频率，而且朝特定方向传播。好，这个是所谓的平面。好，我们上次已经介绍过，说平面波可以写成一个 cosine 的形式啊，然后经过一般表达式的转换，可以把它转换成这个复数的形式啊。So last week we learned that a monochromatic wave is propagating along certain direction. Then we can say this kind of monochromatic wave is called black wave. This word black indicates that the phase, constant phase, is distributed at a certain time. 就是说你把那个同一个相位的点连起来，它就是一个平面。好 ，So if you connect the points with the same phase, this points form a plan. So we call it plan wave.
你那边有吗？
Plan wave. Okay. And for plan wave,
看到。
in addition to the characteristic of the character of single frequency, monochromatic,
这边要拔起。
we have a specific propagation direction. 有一个明确的传播方向。Along the wave vector k, k is equal to n times omega over c times a unit vector. I denote the unit vector as s. Then k can be written as this form. Here n is the refractive index. 好，折射率。那 omega 是所谓的角频率 ，omega is the angular frequency. Usually we call it frequency, but you understand this frequency is the angular frequency. It is different from the usual frequency by the factor 2 pi. Okay? And c is the speed of light in vacuum. So with this expression, if we want to study the vector wave, the electromagnetic wave, we can use the complex representation of this wave. Okay? We know that from Maxwell equation, we can derive wave equation of this form. This wave equation can be derived from Maxwell equation by assuming that P is equal to 0 and epsilon is constant through the whole medium. Okay? Since D is equal to epsilon times E, we can find that divergence E is equal to 0 And the second Maxwell equation, divergence B is equal to 0, can also give us divergence H equal to 0. Okay, because B is mu times H. Here mu is the permeability. These two equations do not give us wave equation, but they give us some constraint on these fields. We will see the constraints later. How to derive the wave equation? The wave equations are obtained from these two equations. These two Maxwell equations. Okay. According to the relation, constitutive relation, B is equal to mu H. This can be written as mu partial T partial H. And this can be written as epsilon times partial T partial E. So now we use these two equations to derive the wave equation for electromagnetic wave. E and wave equation. We noted that according to this equation, curl E is minus mu partial T partial H. We can divide both sides by mu, then obtain this. Curl E over mu is equal to minus partial T partial H. Then, if we take the curl of both sides, since we can exchange the order of space and time derivative, okay, because they are partial derivative. When we calculate some function, calculate the partial derivative of some function, we mean that we change one variable one time and fix other variables. For example, if we calculate this partial derivative, this means that we do this differentiation but fix y. Okay. Now all the quantities in the electromagnetic wave, electromagnetic fields, we have this quantity as a function of x, y, z, t. X, y, z, t. So, for example, I calculate partial t, partial h. This means that I differentiate h with respect to t, but fix r, which means I take the derivative at a specific space point， 在一个特定的空间点上去做这个计算啊。那如果我移来移去，就不是这个结果啊。我任何的物理量，如果我在计算微分的时候，我让它动来动去，它就需要一个修正啊。If I calculate the total time derivative without fixing the space point, I will get a different result. Okay. So, if the H and E are differentiable vector fields, then we can exchange the order of derivatives. So we can write this as partial t partial curl h. Okay. And the curl h is just equal to epsilon times partial t partial e. So this is minus partial t partial epsilon times e. Second derivative, okay? So, in fact, we have derived an equation similar but not equivalent to this equation, okay? We get the equation of this form. Curl E over mu plus epsilon and this. This is the equation we obtain. Then under what condition will this equation become this equation? The condition is mu is position independent. Okay. If mu is position independent, then we will obtain this equation become this equation. 就是说，如果 mu 是 homogeneous 的 if we have a homogeneous medium, which means mu take the same value in the whole medium, then since mu now becomes a constant, then we can factor out this mu and multiply the whole equation by mu. Okay, then我现在把这一行先擦掉，我先保留最后那一行。This is the equation we obtained. Okay. Now, if mu is independent of position 跟位置无关，也就是说所谓的 homogeneous， 我们的介词如果是 homogeneous， mu 跟位置无关的话 ，then mu then we have curl E plus epsilon mu times second time derivative of E equal to 0. And according to vector analysis, curl E is equal to gradient divergence E minus Laplacian E. So we have this equation. Now, since divergence E is equal to 0, this is also caused by the fact that the medium is homogeneous. Because in a homogeneous medium, we have epsilon equal to constant. Since only when epsilon equal to constant can we factor out epsilon here to get divergence E equal to 0. Okay? If epsilon is not constant through the whole medium, then we cannot factor out epsilon from D. Okay, this equation will become this divergence D is divergence
这台换台。
epsilon E.
对你拿一个。
It contains two terms. The first term is gradient epsilon dot E. The second term is epsilon times divergence E. You see that if epsilon is position dependent, we, in addition to this epsilon times divergence E term, we also have this gradient epsilon dot E term. Okay? We can conclude only the sum of these two terms equal to 0. Okay, then in that case. However, if epsilon and the mu are both constant through the whole medium, then we can conclude that divergence E equal to 0, and this equation becomes this wave equation. 就是说，如果是 epsilon 跟 mu 都跟位置无关的话，这一项就没有了。啊，这一项没有，因为跟位置无关的时候，这一项就没有了。那这个又等于0，所以 epsilon 又不等于0，所以 divergence E 就会等于0。那如果 divergence E 等于0，这一项就没有，所以这时候就回到这个 wave equation。啊 ，so this very simple result can be obtained by assuming that epsilon and the mu are both constant through the whole medium. Okay, 好，就是 homogeneous medium. If epsilon and the mu, one of them change with the position, then we will get some ugly equation like this. Like this. Okay. Although this equation looks ugly, if you assume something else, for example, photonic crystal means that the mu or the epsilon or both of them are periodic function of position. Then you can use some additional method, for example, Fourier expansion and something like that, to derive the spectrum, the eigenfrequency of the solution. Okay, then you get so-called photonic band structure. Okay. In the simplest case that epsilon, mu are both constant, we do not need to consider such complicated situation. Then we obtain this simple result about so-called EM wave equation. Okay, 好，就是如果 epsilon 跟 mu 都跟位置无关的时候呢，我们就得到一个这样简单的这个波方程式啊。不过我们在第4章会讲到另外一种情况，虽然 epsilon 跟 mu 跟位置无关，但它跟方向有关。好，in chapter 4 we will encounter another situation. We will encounter so-called birefringent crystal or anisotropic medium. In that case, that we have D is not parallel to E, and epsilon becomes a tensor or matrix. Then we also cannot obtain equation as simple as this one. We must use some different method to obtain the relation between omega and k. 好，那有了这个结果的话呢，好，这边我们再讲一下，就是说，the general result without assuming constant epsilon and constant mu are discussed in the textbook. For example, you can see equation 1.4-5 and 1.4-7. The ugly equation. see in the textbook, there is a very ugly equation, 1.4-7. Okay, this equation is for the case that mu and epsilon are partition dependent. Okay, in fact, this ugly equation is useless because if we encounter such case, usually we use these equations that we do not use this equation. Although they are equivalent, 它们其实是等价的，但是我们通常不会这样用。So now we consider the simple case that both epsilon and mu are constant through the medium. However, you must remember that when we penetrate through an interface between two different mediums, we must use the proper boundary condition to connect the electromagnetic waves, the electromagnetic fields on the two sides of the interface. 就是说，我们如果遇到一个界面分开两个介质的话，那其实代表的是我穿过这界面 epsilon 是变了嘛，变了或者 mu 是变了，所以那个就相当于这个情况那就但是我们其实可以不必这么用，我们只要用正确的 boundary condition 把两边的解连起来就可以了。So if we encounter say something like this, here is a interface separate two regions. In region 1 we have epsilon 1, mu 1. In region 2 we have epsilon 2, mu 2. Then suppose in this region you have this kind of equation. Use mu equal to mu 2, epsilon equal to epsilon 2. In this region you have the same kind of equation, but epsilon equal to epsilon 1 and mu is equal to mu 1. However, if you encounter the situation that you must cross across this interface, then you encounter this situation because now epsilon changes from epsilon 2 to epsilon 1, or mu from mu 2 to mu 1. Since this change is not continuous change, so if you calculate this, you get something here like delta function. Okay, you have a delta function with the direction pointing along this orientation. Okay, 就你遇到的是不连续变化的 epsilon 的话，你硬去微分它的时候，虽然在这边是0，这边是0，但在这边你其实得到一个 delta function。那个 delta function 会去影响结果。但是这一些影响其实等价于我们前面讲过的 boundary condition。This discontinuity, the influence of the discontinuity, in fact, is equivalent to we use the correct boundary condition. 就是我们在前面为什么要讲 boundary condition？ 其实就是说，我在这个介质我都可以用比较简单的方程式去解，然后我在边界上用正确的边界条件把它连起来就对了，就不需要去考虑这个很复杂的方程式，又丑陋的方程式So if we use the boundary condition properly, you can solve the solutions in region 1 and the region 2 separately, and then you connect them with the boundary condition. Then you do not need to consider this ugly, complicated equation. OK， 好，就在那个情况下是不需要去考虑那个。So now we consider the simple situation that epsilon is constant, mu is constant. Then you can derive a similar equation for H field. You will find that the H field also have the same wave equation. So now if we try, you see that this wave equation is a linear equation. Linear equation means that we can sum different solutions to get the different solution. Okay, we can suppose we have E1 and E2 satisfy the same equation. Then if we sum over E1 and E2, then the summation is also satisfying this equation. 就是说，你可以把不同的解加起来，得到一个新的解。You can sum over old solutions to get new solutions. Okay, so if you try the complex representation of E field, say you can write E as exponential I omega E minus K dot R. Each component of E0 may have different phases. Okay. Then if this complex solution satisfies this equation, then if you take the real part also satisfies the same equation. Okay. So now we can use this complex representation of the E field to study the wave propagating problem. 就是说，因为我们用复数去表达在微分时候常常比较简单，所以我们习惯用复数去表达它。当你需要的时候，你再取实部就好。那复数表达式跟实数表达式满足的是同样的方程式。The real representation, the complex representation of the same field satisfy the same wave equation. So if now I substitute this representation into this equation, let me show you how to calculate Laplacian E. Laplacian E is Laplacian E0 times exponential I omega t minus kxx minus kyy minus kz z. However, what is Laplacian? Laplacian is this operator. This operator. So, if you apply this operator into this expression, since here the coefficients are constants, and the exponential I omega t has nothing to do with the space derivative, and the partial derivative with respect to x is just applied to this part. And this gives us the square of minus kx times exponential I kx x. Okay? And this is equal to minus kx squared times exponential I kx x. Similarly for the y partial derivative and the z partial derivative. So finally we have this E0 times minus kx minus ky squared minus kz squared times the exponential I omega t minus k dot r. Okay, and the summation of this 3 square part is just the square of k. So square of k times E field. Okay. And how about the time derivative? Time derivative is very simple because you apply only to this part, and this gives you minus omega squared. Okay, so finally you have this relation minus k squared plus omega squared mu epsilon times E equal to 0. So this means that k is omega square root mu epsilon. This is the wave number. You can also write this as the magnitude of the k vector because k squared is equal to k dot k. So we have the magnitude of the wave number equal to omega times square root of mu times epsilon. We know that k, remember that this expression of plane wave is the generalization of the 1D plane wave, 1D sinusoidal wave, okay? So you know that the magnitude of wave number k is nothing but 2 pi over lambda, okay? K is 2 pi over lambda, and omega is 2 pi over t. T is the period. Lambda is wavelength. T is period. T is period. So the wave speed or wave velocity I denote it as Vp. P means phase velocity is equal to lambda over t. Okay. One wavelength corresponds to one period. The wave propagates one wavelength in one period. So this can be written as omega over k. Omega over k. Okay. However, we know from optics that the speed of light in a medium can be written as c over n. N is refractive index. Okay. C is speed of light in vacuum, N is the refractive index. So we finally get the result that K is N times omega over C。这就是我们刚刚所讲过的就是 K 是等于 N 乘上 omega over C。 K is n times omega over c。好，那we can also find the VP, the relation of VP and epsilon mu. VP is omega over k, but k is omega times square root mu epsilon. So this is equal to 1 over square root of mu times epsilon. So we see that the two parameters, epsilon and mu, determine the speed of light in medium. So in vacuum, we replace mu by mu 0 and epsilon by epsilon 0. So this is the speed of light in vacuum. So from this, we can also identify n is equal to the ratio between C and VP. So n is equal to epsilon r times mu r. Okay. The refracting index epsilon r is equal to epsilon over epsilon 0. This is the relative permittivity. And the mu r is the relative permeability. So usually we have non-magnetic material. In optics and photonics, what we are interested is the wave with frequency as high as about 10 to the 15 hertz. So, at the frequency this high, usually the material has mu r very close to 1. 说物质的磁性呢，在很高频的时候，基本上都是饱和的就是实际上你的 mu 没有什么特别的 mu 因为就 mu r 几乎都是你所看到的什么铁磁性、顺磁性，这些都是在很低频的情况大概在我印象中，大概在100万赫兹左右megahertz 左右的时候，就已经有点接近1了，就已经接近1，就更高很难做出 mu 不是1的东西。当然，近几年流行的 metamaterial 用一些不同的方法去等效做出来，但是天然材料的 mu 是在高频是接近1，所以 usual material have mu r very close to 1 at high frequency. So usually we just assume mu to be mu 0. In this textbook, we just assume mu is equal to mu 0. Okay? So under this assumption, we have n approximated by the square root of epsilon r。好，就说你所看到说折射率等于根号 epsilon r 这个等于的条件是什么？就是 mu r 很接近。好，否则的话其实是要把 mu r 考虑进去的。啊，否则是要考虑进去。啊。So if we encounter non-magnetic material, then you can approximate refractive index of the square root of epsilon r. Okay? So with these assumptions, now we want to know the polarization property of the electromagnetic wave. Suppose we write E as U1 times E0 times exponential I omega t minus k dot r. And write H as U2 H0 exponential I omega t minus k dot r. We want to know the directions U1, U2, and K. What's the relations between them? We can write K as K times, say, U3. 我是可以把这个叫做，我直接把这叫 S 啊。Here U1, U2, and U3 are three unit vectors. We want to know their relations. But we cannot derive their relations directly from the wave equation, but we can find the relations between them from the original Maxwell equations. OK， 好，就在原来的 Maxwell equation 里面提供了比较多的资讯。让我们可以得到它们之间的关系。好 ，So in the complete Maxwell equations, the Maxwell equation provides sufficient information, so we can derive the relations between these three unit vectors and the relations between k and the other quantities. 好，我们下一堂课再来讲这个内容。好，我们这边先下课，下课时间。